Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 3, Waves in Thermodynamics. We're looking at Inquiry Question 5 with these following dot points on focus. So, the lesson intention for today is to define specific heat capacity and define its relationship with temperature changes in objects. By the end of the lesson, hopefully, you'll be able to analyze the temperature changes of objects due to their specific heat capacity. If you want to do a bit more reading, textbook references are here. So let's begin. Okay, so the dot point we're investigating analyze the relationship between the change in temperature of an object and its specific heat capacity through the following equation here. We're going to look at a couple of things. We're going to look at this graph in a bit more detail, and we're going to also look a little bit about the ability to store heat. Think about this for a quick second. When you receive a burn from a hot item, what material would you use to cool down? Would you use solid water, ice, or would you use running liquid water? Which would be the preferred option in this case? Okay, so the question asked for that specific reason has to do with the concept called specific heat capacity. So specific heat capacity, symbol lowercase c, refers to the amount of energy required to raise the temperature of a unit mass of a material by 1 degree Celsius. Okay, it can be measured in a couple of ways. You can measure it in joules per Kelvin per gram. You can measure it in joules per Kelvin per kilogram. Now, for us in physics, we actually use this one here. Okay, so in physics, the specific heat capacity calculations uses this value here. This for grams is used in chemistry. Obviously, the reason being is just because of the size of material we deal with. If you have a look at the heat capacity of helium, it's about 5,193, water is 4,200, and so on. So what that actually means is to heat up water by 1 degree Celsius, you need 4,200 joules of energy per kilogram of water. Okay, that's what it means. So what affects specific heat capacity? There are two reasons. The various forms of energy contribution in the internal energy of the structure. So that could be how the molecule or substance is bending, stretching, spinning, rotating, along with its translational kinetic energy. It could also vary depending on the mass of the atoms and molecules. So copper and aluminium would have a different specific heat capacity based on the mass of the individual, elements that we have here. So that affects specific heat capacity that way. So let's have a look at a heat curve diagram. On the y-axis we have temperature, and on the x-axis we have time, which represents also the amount of heat that's being added in this case to water. Now water is a really interesting case. You can see that as you add heat to water, the temperature also naturally increases. You can see how from ice, minus 20 degrees to 0, there is a little plateau here. This plateau represents the changing from solid water to liquid water. And we'll talk a little bit more when we talk about latent heat, what these things represent. But what I want you to focus on is just the gradients that we see here for ice, water, and steam. You can see for ice and steam, its gradient is rather steep. With water here as the example, the gradient is less steep. Okay? What we can infer from this is it actually takes a longer period of time to make the temperature of water increase in comparison to ice and steam. So let me write that down. as we said, the less steep the gradient, the more energy would be required in terms to be applied to the body in order to make it increase by temperature. So what that would conclude to us is using ice would be less effective to patch a burn than water, because we're actually the consequence of water can help actually release some of that or absorb more of that heat for you. Okay, we'll talk about that in a little bit more context, but let's just firstly look at how this chart works. So we said that during a phase change, energy is being used to overcome the intermolecular forces. So this is why we see a sort of flat line here. In the process of vaporization, we see that there will be a complete separation of the intermolecular forces. So say for water, we imagine as a solid, the particles are really closely packed together, not absolute 7 level, but they'll be closely packed together. As we increase that temperature, the particles are starting to vibrate a lot more. And as they vibrate, they're going to begin to separate from each other. When they reach the phase of vaporization, or in this case, the gas phase, then the particles have completely separated from each other. As you can see, the consequence of increasing temperature within the system. So, specific heat capacity, let's revise this idea again. You might have seen a demo like this before, where a person's holding a bit of detergent water and they light their hands on fire. Now, in this process, there's a little secret thing that people do that you don't actually see, and that is they apply a bit of water on their hands. Now, the reason why they do that is because water, as you can see, has a really high heat capacity. Compare that with ice, which has a much lower heat capacity here. So the reason why we tend to say if you get a little burn on your hands, you use water and run it through for a couple of minutes, it's because water absorbs heat really well. It takes a lot more energy, so a lot more of that heat energy, to make that water get warmer in comparison to ice. And obviously if you have a tap running water, then you have a constant supply of water that's just extracting more and more heat away from you. This is also the exact same reason why we humans sweat. When we sweat, we give out, water molecules. And when we release that sweat, the water molecules also carry heat from our body. So by carrying that heat away from our body, and then when it evaporates, we essentially give off heat through the process of our sweat with liquid water in it evaporating into air. Okay, so what could be other ways that could affect how well heat is transferred? Well, we know that firstly, the temperature will go higher if we add more heat. So change in temperature will affect the quantity of heat that is transferred from one object to another. Okay, it could also be related to the mass of the object. So if we have a bigger mass object, so if we compare 100 grams of water, let's say, we have 100 grams of water and we have 1 kilogram of water, then we're going to say that the 1 kilogram of water will transfer more heat because there's more particles to do that transfer. And obviously the last one is the specific heat capacity, and that's the object's ability to store heat inside its bonds and all those internal energy kind of stuff there. So the formula we actually use to describe the relationship between temperature and specific heat capacity is this formula here. Okay, so we can find that the amount of heat that's transferred from an object or to an object is related to its mass. That's measured in kilograms. Its specific heat capacity, which is measured in joules per kilogram per Kelvin, and the overall temperature change. Now, for this specific example, it doesn't really matter if the temperature change is in Kelvin or in degrees Celsius, because we're just looking at a ratio change here. We don't have to do any conversions here. So what we can say is that the temperature, the change in temperature is directly proportional to the heat transfer. But if we look at comparing the heat capacity and the change in temperature, we can see that there is sort of a inverse proportional relationship. So if we assume these were all constants, this is a constant, this is a constant as well, we can see that specific heat capacity is inversely proportional to the temperature change. Okay, so if we have a really big heat capacity, so if C is large, okay, we can see from this thing here, the change in temperature would be low. And so that's the relationship that heat capacity would have with change in temperature. Alright, so that's enough explained. Let's go on and do some calculations. Question 1, we have a hot water tank containing 135 liters of water. Initially the water was at 20 degrees Celsius. Calculate the amount of energy that must be transferred to the water to raise the temperature to 70 degrees Celsius with a specific heat capacity of that. So, assuming that water has a density of 1, so the amount of liters equals the amount of kilograms, then we can substitute it into our formula here. We have 135 kilograms times our heat capacity of 4,200 times our temperature change, in this case from final to initial. So this is our final, that was our initial, so 50 degrees. The value we get from this, if I just quickly plug it into my calculator, (2835) and then 40 joules. Okay, so that's the value we get there. And then in question 2, we said a bath has 75 liters of water. Initially the water is at 50 degrees. How much energy would have been transferred if the bath cooled to 30? So in this case, we've released energy. So we just account for that. 75, 2000, or 4,200, and then 50 minus 30. Or you could do it the other way around, so 30 minus 50, let's do it this way. And so we get a negative value of 63,000,000 joules. Now this negative represents heat released into the environment. Okay, there's nothing wrong with having a negative value of heat in these kind of calculations. It just represents where the heat has gone. In question 1, heat has gone into our system to make it warmer, while as question 2, heat has gone away from our system to make it colder. So that's the difference there. Alright, question 3. You're designing a electronic circuit element which has 23 milligrams of silicon. The electric current through it adds energy at a rate of 7.4 milliwatts, which is joules per second. Your design doesn't allow any heat transfer out. What rate does the temperature increase by if we have a silicon element of that specific heat capacity? Well, same idea as always. Let's write out our formula. Okay, we have 23 milligrams, which is 10 to the minus 6 kilograms. We have 705 specific heat capacity, and we're trying to find the change in temperature. The overall heat that's being transferred in is 7.4, 10 times the power of -3 joules per second, so we can leave it as that. We can make T the subject of the equation, so we can move everything across. Alright, so 0.4563675. Kelvin. If you want to round it off, the lowest sig fig we used was 2, so we can round it off to 0.46 Kelvin. And that's the increase we saw there. The final question we're going to look at is a particular chef using 200 grams of cold water with a temperature of 15 degrees, puts it into an aluminium source of about this, and then it rises to this temperature of 120. What will be the common temperature of the water and saucepan when thermal equilibrium has been reached? Now remember, when we reach equilibrium, the temperature of the two objects will be equal to each other. So how would we write it? We are going to say the amount of heat from the water will equal to the amount of heat transferred to our aluminium. So let's quickly write out an equation. MC delta T, that's for water, and then we have MC delta T, that's for aluminium. So we'll just write aluminium, we'll just write water on these two sides to label the difference. The mass of the cold water we're using is 200 grams, so convert that into kilograms. The specific heat capacity of water we already know. Alright, so in this case we're going to write the temperature we reach is T subtracted by 15. Now the reason why we want to say that is because this is cold water mixing with a hot piece of aluminium, which means heat from the aluminium is going to be transferred to water. So the water should have a net increase in terms of the heat energy. So T should be a much higher value than 15. So if it's bigger than 15, we have a positive value. And that's being consistent. So which means with the aluminium's case, if we write our equation along, the overall temperature we're going to reach in this case is going to be subtracted by it. So T would be the temperature we have there. Okay, so this is the original warmer temperature, and we're going to get to a lower temperature overall in that case. So rearrange the formula and see what values you get from that. Right, so what we find is the overall temperature once thermal equilibrium has been reached is 37 degrees Celsius between the two objects. Alright, and so that concludes the first part of this lesson where we talk about specific heat capacity. Hopefully you have a better understanding of the relationship between temperature and heat capacity, how heat capacity of an object will increase or decrease the likelihood an object can be increased in temperature or decrease in temperature faster. Now, thank you for joining in the classroom. We'll see you again next time. And please give a like and subscribe.